Hello. This is a quick follow-up to video 24, also known as video 25. And by our observation, I hope we've realized, you know what? Even though this is the good, solid, concrete, standard way to do it, canonical SOP, we don't have to do all that. We can get away with less circuitry and get it implemented faster, and it runs faster, all those good things. But we need a formal technique, and here it is, technique, T-E-C-H-N-I-Q-U-E. Technique for, specifically for SOP, which is circuit design simplification. It's called a Karnaugh map. K-A-R-N-A-U-G-H. And yes, friends, computer science is still a young enough field that if you do something clever, then your name gets permanently attached to it. And you go viral and you will live forever. You will gain computer science immortality, just as Mr. or Dr. Karnaugh did. Karnaugh map, and I struggled to write at that time. I'm not going to do it again. It's also called a K-map. Like K-pop, except with a map. This is, I'll briefly define it. Definition, a K-map. I'm going to call it a special rewriting of the truth table, because really that's what it is. A K-map is a special rewriting of a truth table in a different format. That's why it's a special rewriting. Why do we do that? To reveal, I'll call them variable values. Yes, I'm making up this definition as I go along. A K-map is a special rewriting of the truth table to reveal variable values that don't matter. What do we do with things that don't matter? We ignore them. We don't include them. We leave them out because they don't matter. Where's an example? Well, look in the last video, there's an example. Here, C is going to get left out. When we reduce these two products down to one even smaller product, we leave out C. Because C, it can be off, it can be on, off on, off on, off on, flip back and forth, doesn't matter. We realize that if A is on and B is on, if those are both ones, then the value of this sub-expression here in the SOP, that's going to be 1, regardless of the value of C. And that's exactly what this is talking about down here. Here's an example of a K-map. It looks like kind of like an egg carton. At least to me it does. It's a grid with 8 squares. Count them. 1, 2, 3, 4, 5, 6, 7, 8. And a strange little line up here. And I'm going to put lowercase a over to the left to label these rows correspond to A. The columns correspond to the combination B and C for 2 variables. And I know that doesn't make any sense, but I'm going to try to sneak up on sense here. 0, 1. A value 0, A value 1. BC, that's 2 digital logic variables, 2 binary variables. So there are 4 possibilities. How handy. We'll label the columns with the different values of BC. Now watch this carefully. Be careful. Don't get ahead of me. 0, 0, 0, 1, 1, 1, 1, 0. An extra for experts in a different color. That's actually called gray code. There we go again. A famous computer scientist came up with this clever way to write the binary numbers in that order. That's called gray code order. G-R-A-Y-C-O-D-E. Gray code. Not because it's gray, because it's because it was the guy or the gal's name. What's special about gray code order? Well, if we look at these columns, and please look at them with me. As we go from one column to the next, the label at the top of the column differs in only 1 bit position. Only 1. 0, 0 to 0, 1 differs in what the value of C is. So this column here corresponds to when B is 0, C is 0. This is when B is 0, C is 1. The next one over is not the one in the next numerical order. No, no. Gray code says you can only change one bit going from the column to the next. So going from 0, 1 to 1, 1, we change the value of B from 0 to a 1. See how to play this game? Then the last one, going from 1, 1 to 1, 0, we change the second bit. We change C from a 1 to a 0. Oh, did I say the last column? Here's where you've got to stretch your mind and visualize things. Wrap this around like a cylinder, like an oatmeal box, or the cardboard tube inside a roll of paper towels. If we wrap this around, and that's actually what it's called, wrap around, then we can visualize in extra three-dimensional space that this column is actually also next to that one in gray code order. Why so? Well, they only change in one bit. 1, 0 to 0, 0 changes the value of B from 1 back around to 0. So it's almost like we've got an infinite set of columns next to each other, where each one is next to the next one. No, each one differs from the next one, and it's labeled by only one bit. And that might seem like a weird thing to even try to visualize. It actually comes in handy, as we'll see fairly soon. Same thing here, but this much less interesting wraparound. 0, 1. And we can think of this continuing indefinitely as well. 0, 1, 0, 1, 0, 1. So this one, that's going to look more like the paper towel roll, isn't it? If I fold the whiteboard and roll that up into a cylinder. That was an awful lot of talking about nothing but the labels here. What we want is a K-map, a special rewriting, which means it's going to have exactly the same information here, except I'm going to leave off the zeros. That's not my invention. It's just, that's typically done, a convention. Leave out the zeros in this truth table. 0, 0, 0, that square is right here, the top left corner, just where it belongs, but we don't put anything. The first place where we put a 1 is square 0, 0, 1. 0, 0, 1, right there. Ah, yes. And now you can zoom ahead and fill in the whole table. That one's blank. The next square that has a 1 is 0, 1, 1. 0, 1, 1, right here. And then 1, 0, 1. 1, 0, 1, right here. 1, 1, 0. 1, 1, 0, way over here. They're next to each other over here in this truth table, but not in that one. Oh, but we filled it in anyway. 1, 1, 1. That's this square right here. There we are. If I did that correctly, and I hope I did, then that holds in this sort of folded format. That holds exactly the same information as our original truth table. Why do we do it that way? Well, watch this. Remember up here, pretty in pink, those two expressions? Let's see. This was 1, 1, 0, 1, 1, 0, and 1, 1, 1. 1, 1, 0, 1, 1, 1, right there. That pink square bracket corresponds to this pink oval shape down here. Those two ones are next to each other. And look what they tell us. They tell us more directly that if A is 1, let's ask ourselves this question. Here's a way to do this. What do these two ones have in common with respect to the inputs? Well, A is 1 for both of those. What else is true? B is 1 for both of those pink circled ones. What's not true? Well, they don't have a value of C in common. Here we see C, bless its heart, flipping back and forth like there's no tomorrow, trying to change the value, but it just can't. C goes from 1 to 0, 0 to 1, 0 to 1, toggling back and forth. And still the output will be 1 because A and C are both 1. Now, that one was actually fairly easy to map because those two are right next to each other in the SOP. They're next to each other down here. And what was that? I'm going to just do this incrementally. You put a little R out front because this is not canonical anymore. And for those of us that don't like to keep up with things that have to be in order, since it's reduced, it doesn't even have to be in the order it would show up in the truth table. That's more or less meaningless now. We just want to make sure we get all the ones represented on our reduced SOP. This would correspond to the product A is 1, B is 1, A dot B, the end. That's not all the ones. Look at this. Be amazed. I hope the green writes. We could keep doing that, circling pairs of ones and so forth. But it turns out, and I'll have to go into this in some more detail later, maybe this is the hardest part of the whole thing to explain. We are looking for collections of ones that are adjacent to each other. In other words, they share a side. Catty corner doesn't count. These two are not adjacent to each other. These two are. We're looking for collections, whole sets of ones, that are a power of 2. And if powers scare you, then the power of 2 is, those are the things that we use as labels on our truth table, or our binary truth table. We're looking for collections of ones that are 2 ones together adjacent, 4 ones together, 8, that would fill up the whole table. There's no point in going any further. If we had a gigantic K-map, maybe we look for a group of 16. They're all adjacent to each other. That's all to say this. Those 4 ones, those are all adjacent to each other. Those all have something important in common. Even more important are the things they don't have in common, because those could be left out. So our OR, to pick up all the other ones in that special kind of truth table, the green expression, I need to have an expression that represents what's going on with all 4 of those ones. What do they have in common, I ask myself. I'm just going to have to remember to ask myself that every time when we're doing one of these. What do they have in common? A value of A. No, they do not. A is flipping back and forth between 0 and 1. Those 4 ones don't have a value of A in common. What about B? Well, no. B is flipping back and forth between 0 and 1 as well. They don't have a value of B in common. What do they have in common? The value of C. Look at this. C is 1 for that column. C is 1 for that column. C is 1 for both of those rows where those columns are next to each other. C. That's it. That's the reduced SOP. Talk about reduced. We didn't watch this on the stove. It boiled away to almost nothing. Look at this. We've got one dinky little 2-way AND gate, one dinky little 2-way OR gate. We don't need any knots at all, and we have represented this entire logical function. This is a reduced logical function for function f1 that started off as our truth table way over here. It's just amazing. You know what? That's so small. We haven't done one of these in a while. That's so small I could even draw the whole thing if I wanted to. Look at this. I didn't leave any room, but I'm going to draw it over there anyway, and I'm going to draw it in purple, hoping that it will show up. A, B, C. I need all 3 inputs. Sometimes you get to even leave out an input variable. A, B, C. A and B, that's an AND gate. And whatever comes out of the AND gate, I OR that with C, so I need an OR gate. And the output is the value of function f1. Wow. Yeah, we could do that logically in about 30 seconds. Much quicker than this. Far fewer gates, only 2 gates required. And it does all of this. All of this. I don't know, I don't trust it. That's just too good to be true. Let me pick a random row here. How about this one? A is off, B and C are both on. A is off, well the AND gate's off. B and C are both on. Well, C all by itself, that's enough to make that OR gate spit out a 1. So yeah, that works. Let's try a negative one. What about 1, 0, 0? 1, 0, 0. 1, 0. If B is 0, then that output is 0. And if C is 0, then we got 2 zeros going into the OR gate. Now that's not a proof. I would want to try it with all of these just to double check and triple and quadruple check and make sure. But that is exactly a circuit to implement this rather than following this no shortcuts recipe up here. Amazing how that works, isn't it? That is so amazing, and for us it is so important that I think I'll do a video just of examples, and I'll let you reflect on this until video 26, which is going to be hot on the heels of this one. See you online.